Hi, I am a tutor in Uplatz. Today we are going to discuss about introduction to software performance engineering. Hardware acceleration technologies. We have the Pentium 4 Intel chip. Uh, we have the Pentium 4 put in multi-core. We have the supercomputing, high performance computing facility. High performance computing facility calculator. Intel Core 2 Duo processor, CPU core and L1 cache, dual core CPU core chip consists of CPU core L1 cache and CPU core L1 cache and through bus interface and to L2 cache and around the rest of the things. We have the NVIDIA multi-core processor board. We have the multi-threaded wide SIMD, ISTS, multiple of them, and connected through L2 cache. On another one side, it is structured logics and fixed function with memory controller. On the other side, system interface, display interface, and memory controller. A board consisting of such a processor, Intel Core 2 Duo quad processor or diagram is shown here. It has got 4 cores with each L1 instruction cache and L2 L1 in data cache and they are integrated through L2 to the main memory. L1 data cache size 32 KB, line size 64 KB, latency 3 cycles, associated activity 8-way, L1 instructions cache 32 KB, 64 line size 64 bytes, latency 3 cycles, associated activity 8-way, L2 cache size 6 MB, line size 64 bytes, latency 4 cycles, associated activity 24-way. Hierarchy consists of registers, then L1 cache, L2 cache, memory, disk, tape. In registers, instruction operands, and L1 cache blocks, L2 cache blocks, memory pages, disk files, capacity, access time, cost, CPU register 100 bytes, 300 to 500 picosecond, 0.3 to 0.5 nanosecond, L1 and L2 cache, 10 second to 100 second kilobytes, approximately 1 nanosecond to 10 nanoseconds, cost 100,000 second per gigabytes, $1,000 second per gigabyte. Main memory gigabytes, 80 nanosecond to 200 nanoseconds, cost $100 per gigabyte. Disk 10 seconds, T bytes 10 millisecond, 10 million nanoseconds, $1 per gigabyte. Tape infinite, second minute, $1 per gigabyte. Staging X per unit. Faster program compiler 1 to 8 bytes, cache control 32 to 64 byte, cache control 64 to 128 byte, OS 4K to 8K bytes, user operator in megabytes at the lower level. And on the faster and lower, smaller and larger is from register to tape is larger. Software performance engineering. Why is performance important? Acceptable response time, anti-lock break system, MPEG decoder, Google search, etc. Ability to scale from 100 to millions of users, documents, data, use less power resources, viability of cell phone dictated by battery life, etc. Improving performances are knowing that there is a performance problem, complexity estimates, performance analysis, software tools, read the generated assembly code, scalability testing, comparison to similar programs, experience and curiosity, establishing leading cause of the problem, examining the algorithm, data structures, the data layout, understand the programming environment and architecture, eliminating the performance problem, redesign the algorithm, data structures, and then write programs close to the metal, C++, adhere to software engineering principles, simplicity, modularity, portability, golden rule, be reactive, not proactive. And remember the same picture, hierarchy of register to tape with L1, L2, memory and disk in between. A case study of matrix multiplication, MMM, A equal to B into C. For unit I is equal to 0 to I less than X, I plus plus. For unit I, J is equal to 0 to J less than Y, J plus plus. For unit K is equal to 0, K less than Z, K plus plus. A of I, comma J is plus equal to B of I, comma K, source A of I, K, comma J. Matrix multiple is a fundamental operation in many computation, video, encoding, weather simulation, computer graphics, etc. The following case was studied by Professor Sam and Amersinghe, MIT. Application developers in the industry write that kind of code. 2 years of personal experience with student internships in the University of Lille, France. Matrix values, matrix row, integer row, double row. I did like my matrix representation of object oriented, immutable, represent both integers and doubles. Value, a class for matrix coefficients, matrix, a class of matrices, matrix row, an abstract class for matrix rows, double row, a concrete class for matrix rows, matrix multiply, a class for testing matrix multiplication. MMM Java code value class, public class value, final matrix type, final init ival, final double dval, value unit I, init get init throws exception value, double D type matrix type dot floating point, D value D, I value 0, double get double throws exception if type equal to matrix type dot floating point, return dval, else throw new exception. Matrix Java matrix multiplication, matrix multiplication Java code matrix class 1/2, public class matrix, final matrix rows, final init and rows and columns, final matrix type, matrix init rows, init columns, matrix type. This dot type is equal to type, this dot end rows is equal to this dot end column is column, this dot rows is equal to new matrix row, this end rows. For init I is equal to 0 is I less than this dot end rows, I plus plus, this dot end rows of I is equal to type equal to matrix type integer, new integer row, this columns, new double row, this columns. Matrix class 2/2 Java code, public class matrix, private matrix row, rows, matrix type, I unit rows, n rows, unit n columns. This dot rows is equal to rows, this dot n rows is equal to rows, this dot n column is n column, this dot type is equal to type, public matrix update, init row, init column value val, rows expression, matrix row, new rows, new matrix n row, matrix row and rows. For init I is equal to 0, I less than n rows, I plus plus, and new n rows of I is equal to I equal to row means row of I dot update column comma value row of I colon row of I returns new matrix, new rows, type n rows and columns, value get init row, init column, throws exception, return rows of row, dot get column. Abstract class matrix row, public abstract class matrix row, abstract value get init column throws exception, abstract public matrix row update init column value val throws exception. Double row class public class double row extends matrix row final double the row public final init new columns double row init new n columns. This new columns is equal to n column. The row new column new double n columns for init I is equal to 0 I less than n column I plus plus 0 of I is equal to new double of 0 private double row init columns. This the row equal to row. This the num columns is equal to columns. Public matrix row update init column value val throws exception double row new double and num columns for init I is equal to 0 I less than num column I plus plus row of I is equal to I equal to 0 smart new double value dot get double colon the row of I new return new double row of comma new columns num columns public value get init column return new value the row column. Matrix multiply class public class matrix multiply public static long test init x init y init z matrix A to matrix x comma y comma matrix type floating point matrix B new matrix y comma z comma matrix type dot floating point matrix C new matrix x comma z comma matrix type dot floating point long started is equal to system dot nano time try for init I is equal to 0 I less than x I plus plus for init I j is equal to 0 j less than y I j plus plus for init k is equal to 0 k less than z k plus plus a is equal to a dot update I comma j new value a dot get I comma j dot get double plus b dot get I comma k get double star c dot get k comma j get double. Catch exception key long time is equal to system nano time long time taken is equal to time taken minus started system of contain time plus time taken divided by 1,000,000 plus millisecond return time taken. Java code performance, it took almost 5 hours to multiply 2024 by the matrix on a PC with a single core running at 3.15 gigahertz, thus providing 3.15 into 10.9 cycles per second. Each inner loop iteration performs 1 multiply, 1 add, and 3 index updates and 1 branch check. So 6 hours total, 6 into 10 to 24 cube is equal to 6, 442, 450 into 944. That comes to about 8358 cycles per each visible operation. How can we improve performance? Find out where you are spending your time. A lot of interesting information. Time spent, cumulative time spent, number of calls, etc. If 90% time is in one routine, inefficiencies in the rest of the program don't matter. Are the hotspots ready doing what you expect them to do? Method Java lang double init double number of calls 3,000,000 method type 2,100 double row init 3,072 51,128 method time commodity time 102,980 double row dot update init value 11,535 31,630 32,610 matrix multiply test init 0.1790172,410 double row get init 34,695,1290,1870 matrix get init 34,695,1170,3040 value get double 46,140,1,000 value init double 46,140 810 double row init double init 11,535 3,480 matrix row init 14,607 222 matrix init matrix row matrix step init 11,534 190 190 matrix init matrix step 340 103 around 3,020 main init 110 172,040 root dash 172,040 main string 172,040 Java lang object init 72,285 Java lang system nano time 1 so on up to Java lang enum string init 2. Issues with immutability to update one coefficient in a we copy the word row. This implies huge memory footprint allocation, deallocation. Can we do better? Matrix class revisited. The program for the matrix class is again visited, repeated here. Double row revisited. So we put the double row class. Then we have millisecond immutable is 17,094,152. Mutable is 77,926. Together it is 219.7x. Cycles per operation is 8358 and 38. So the profiling data for the book code is given here. Issues with dynamic dispatch method call override. Each method call needs to look up the object type. Dynamic dispatch is an address plus an indirect branch. Indirect branch are costly. Most processes are deeply pipelined. 12 pipeline stages in code, 2 Duo, 20 in Pentium 4. Yes, the processor needs to be able to keep fetching new instructions, next instruction before executing them. For the direct branch, the target address is known. For an indirect branch, the process needs to wait until the address is complete. Can we do better? Double matrix class and the double matrix class final the double rows final init and rows and columns matrix init rows init column this rows this column this rows new double row this end rows for init I this end rows I plus this rows I new double row this columns and columns y set init row column double v row rows of row dot set column comma v double get init row init column return rows of row dot get column. The class and double row instead public final class double row double the row public final init and num columns double row init and column this in num columns and columns this the row new double and columns public void set init column in double value throws exception and the row column value public double get init column throws exception return the row column. Here we have got immutable, mutable, and double only with additional 2.4x. We get and another 219.7x. So totally we get 522x. So cycle of operation is cycles per operation is 8358, 38, and 16. The profiling for this is shown here. You can see some improvements. The performance for stage 1 to 3 for immutable, mutable, and double are shown in this figure. Issues with objects, memory fragmentation. Objects are allocated independently all over the memory, contiguous in memory, then getting to the next is just an index increment. Method call override. Method calls are expensive. It is hard to optimize the body because of the method call. MMM code, no objects, double A, new double X, comma Y, double B, new double x comma z double c new double z comma y long started system dot nanotime for unit I is equal to I less than x I plus plus for unit j is equal to j less than with j plus plus for unit j k is equal to k less than z k plus plus a of I comma j plus equal to b of I comma k star c of I comma j long ended system nano dot nanotime. Java performance stage 4 we have now immutable mutable double only no objects, so we get a total performance 219.7x 2.2x plus 2.4x plus 219.7x 520, so totally 1117x 8358 38 6 and 7. From Java to C code, in Java, memory bound checks, write code compilation and dynamic compilation, possible and no time to generate the best code. In C, no memory bound checks. Intel C compiler compiles the program directly into x86 assembly code. The typical naive C code is shown here. Okay. Double star star A, double star star B, double star star B, unsigned integer session T. Started ended time taken. Init I comma j comma k a double star star malloc memory allocation is done. Then for loop 3 for loops are taken. Then to allocate the memory. Then afterwards we do the matrix multiplication using the 3 loops. Then we calculate the time. So we have immutable, mutable, double only, no objects in C. So we get a performance of 2271x, reducing from 8358 to 38 to 16 to 74. Modern hardware counts events, CPI clock cycles per instruction. The number of clock cycles that happen with an instruction is being executed. With pipelining, we can improve the CPI by exploiting instruction level parallelism, L1 and L2 cache miss rate, instruction retired. In the event of a misconception, instructions that were scheduled to execute along with the mispredicted path must be cancelled. We remember the picture from register to tape. C code issues with matrix multiplication equal to B cross C. Contiguous access are better. Data fetch as cache line and code duo 64 byte L2 cache Li. With contiguous data, a single cache fetch supports 8 3 doubles. Transposing the matrix C should reduce L1 cache misses. Preprocessing the data, we do the preprocessing of the data as shown in this code. Once you do the transpose in C, it becomes 7514x. Okay. Then we have in C, CPI 4.78, transpose 1.135x improvement, L1 miss rate 0.24 to 0.52x improvement, L2 miss rate 0.02 to 0.02. Percentage is 43% to 53%. Instruction retired 13,137,280,000 to 13,001 for 86336. The processor 1 process 2 1 cycle, L1 3 cycles, L2 14 cycles, L3 100 cycles plus cycles, memory gigabytes. The memory system dilemmas: a small amount of memory implies fast access, large amount of memory implies slow access. Workaround: programmer stores more portable probable access in caches. Order heuristics determine what will be in each cache and when. Blocking for optimizing data reuse, name calculation of OA, show computing 1000 quotient, 1000 access in A, 394 in B, and 1000 394 for 393.160 in C, total 394 524. Computing Z2 by Z2 block of A, so computing again 1000 quotient, 1000 access in A, 384 into 32 in B, and that 28 NC, total 25,600. The iteration space is traverse so as to reduce memory accesses. Blocking, we use started read timestamp counter for j is equal to 2, j is equal to 0, j2 less than y, k is equal to k2 is equal to 0, k2 less than z, and j2 for I is equal to 0, I less than x, I plus plus for j is equal to j2, j less than min of j2 plus block of x, y, comma, j plus plus for k is k2, k less than min k2 plus block y, comma, z, k plus plus, I and d, j, I, j, y plus equal to I and d, b, I, k, z, star, I and d, c, k, j, z, ended, read timestamp counter, time taken, ended minus total, time taken. In the stage 7, we get the performance improvement of 12,316x. We use the tailed one as well. In C, we get CPA 4.78, transpose 1.13, tail it becomes 3x better, 2.49. L1 miss rate is reached 0.02. L2 miss rate is 0. Performance is 36%. Instruction retail is more than 18 billion. Modern processors have made many performance instruction level parallelism. MMX SSC instruction do the same operation on the multiple contiguous data at the same time, prefetching of data, nudge the computer, remove any perceived dependence, bound most constant variable to constant, possible use of compiler progmas, play with the compiler flags with reporting generators and tweak the program until the compiler is happy, or use the tuned library BLDAS. Nudge the compiler program is shown here. After nudging, tailed vectorize and VLSM, we get that is the 43x improvement. CPA is brought down to 0.37. L2 miss is L1 miss is brought down to 0.02. L2 miss is 0, and percentage instruction has gone to 78%. Retired also improved, reduced. Thank you.